In the previous video, we had general discussion about aramid fibers. In this video, we will discuss about meta-aramid fibers, their synthesis or polymerization, fiber spinning, properties, and their applications. In meta-aramids, phenylenediamine and amide units are linked in meta position, which results in irregular chain conformation and comparatively low tensile modulus or tensile properties compared with para-aramids. We can see the reaction where metaphenylene diamine monomer reacts with isophenol chloride monomer and polymetaphenylene isophenylamide meta-aramid is obtained along with generation of hydrogen chloride. The polymer is prepared through low temperature solution polymerization or interfacial polymerization according to the reaction shown here. Aromatic rings in the structure of meta-aramid are parallel but are not coplanar. In solution polymerization, the aromatic diamine is dissolved in an amide solvent like N-dimethyl acetamide DMA or N-methyl 2-pyrrolidone NMP, and a stoichiometric quantity of aromatic diacid chloride is added to the diamine solution while stirring vigorously. Since reaction is highly exothermic and therefore the rise in temperature will depend upon the concentration of the diamine monomer in the solution and degree of cooling. Since high temperature can lead to side reactions that can result in polymer ends that are unreactive, therefore the reaction must be carried out at low temperature. The scheme of the polymerization, low temperature solution polymerization is shown here. 9% solution of metaphenylene diamine in dimethyl acetamide is prepared and is cooled to -15 degrees centigrade before it is mixed with molten acid chloride in the mixer. Here the polymerization reaction takes place since reaction is highly exothermic, which brings the temperature of this mixture to 74 degrees centigrade. In this reaction, because HCl hydrogen chloride is formed, which is neutralized by calcium hydroxide, but before neutralizing this acid with calcium hydroxide, the heat is removed by heat exchanger. Then the formed polymer is blended, deaerated, filtered, and finally sent to the storage for further processing to be synthesized in the form of fiber. Another method through which polymer can be synthesized is interfacial polymerization. In interfacial polymerization, the reacting monomers are dissolved in a pair of immiscible liquids, one of which is usually water. So, for the synthesis of meta-aramids, isophenol chloride is dissolved in solvent like tetrahydrofuran, which is immiscible with water, and then the aqueous solution of metaphenylene diamine is mixed with it with vigorous stirring. The aqueous solution contains a base that neutralizes the HCl that is generated, since during the polymerization reaction HCl is formed, which is neutralized with a base. Polymer formation takes place at or near the liquid-liquid interface when the two solutions are brought in contact or stirred together. Since the two solvents are immiscible, therefore monomers in both the solutions will react at the interface of the both the solvents. In both the methods, whether it is interfacial polymerization or solution polymerization, higher molecular weight polymer is obtained through interfacial polymerization, which results in improved properties of the fibers, because we know higher the molecular weight of the polymer, higher will be the superior will be the properties of the polymer. This process, interfacial polymerization, is used by Tejan to produce meta-aramid fiber known as Tejan connex. Whether it is polymer synthesis through solution polymerization or interfacial polymerization, the two factors that affect the nature of the reaction are use of high purity monomers and stoichiometric balance of the two parent monomers. This is the scheme of the interfacial polymerization. In this scheme, metaphenylene diamine is dissolved in an amide solvent in a dissolver and then mixed with isophenol chloride, where reaction takes place between the two monomers to form the polymer. The polymer is then washed with water and solvent, and water is then recovered. The polymer is then dried and sent to the storage for the spinning process. After synthesis of the polymer, the polymer is sent to the spinning process, where fiber formation takes place. We know that most of the aromatic polyamides, almost all the aromatic polyamides have high melting points, and therefore they cannot be processed through melt processing because they decompose before their melting temperature is reached. Due to this reason, their melt processing is not possible and their solution are processed for fiber spinning. The techniques which are used to make fibers from meta-aramid solutions are wet spinning technique and dry spinning technique. The fiber can be formed either through wet spinning or dry spinning. In wet spinning technique, the dry polymer is dissolved in an organic solvent at low temperature and then heating the dispersion to near 100 degrees centigrade to form a clear solution, and then the solution is wet spun into the fiber in an aqueous solution containing a high concentration of an inorganic salt, and the spun fiber is then washed with water, and then solvent and water is sent to recovery, and formed fiber is then dried and any post treatment is performed. In wet spinning, the spinning takes place in an aqueous solution, and the scheme of wet spinning process is shown here. We can see that the polymer solution is fed here, and then this solution is pumped through a filter to the spinneret. The filter is placed between spinneret and the solution tank so that any particle that can block the holes of the spinneret is filtered out. And since this is a wet spinning process, therefore we can see that the spinneret is placed in an aqueous solution bath, where the formed fiber are then exposed to a wet aqueous solution, due to which this technique is known as wet spinning technique. The fibers or filaments that are formed in this process are then stretched here in this stretching zone, and then they are washed to remove any remaining impurities of the process, and then if we need to apply any spin finish, that are applied here, and then the fibers or filaments are then dried, and finally they can be taken up on a package in the form of filament, or they can be cut into the small fibers like staple fibers. The other method through which fiber can be formed is dry spinning technique. In dry spinning, the polymer solution is formed in dimethyl formamide, and then this solution is spun in fibers, where the spun fibers are exposed to dry environment instead of any wet environment. Here in this chamber we can see that the filaments that are extruded through the spinneret are exposed to hot air, where this is evaporation chamber, where evaporation of the solvent takes place, and in this heating jacket the formed filaments are dried, and then these filaments are can be wound on the spool. Post spinning processes can be performed on the fibers or filaments. In the case of meta-aramids, the most important post spinning process is whether to cut the fiber or to keep it in the form of filament, because aramid fibers are available in the form of staple, flog or pulp. Therefore, if we need to cut the fiber after spinning process, the fibers can be cut into various cut lengths according to the requirement. These cut lengths can vary from 1 mm to over 100 mm, and if the fiber is cut in the cut length range of 1 to 6 mm, this is referred to as flock, whereas the longer fibers, for example 38 mm cut length, are called staple. In this table we can see the properties of meta-aramid fibers. In this table, 3 meta-aramid fibers are compared, one nomex by DuPont and the other two from Tejan-Connex. We can see that the equilibrium moisture content of these fibers is in the range of 5.2, and this is a little bit higher than para-aramids. Since we know that meta-aramids have less crystallization than para-aramids, therefore moisture retention for meta-aramid is higher than para-aramids. As far as their tensile properties are concerned, we can see that tensile properties of meta-aramids are comparable with those of commodity or conventional fibers. The limiting oxygen index of meta-aramids is 28, and for Tejan-Connex fibers is in the range of 29 to 32. So we can see that this fiber is thermally stable. The tensile properties of meta-aramid fibers at different high temperatures is shown here, and we can see that up to 250 degrees centigrade it can retain its tensile properties. Here we can see that after a particular number of hours at different temperatures, the percentage of strength that meta-aramids can retain. So we can see that if we expose for 100 hours at 180 degrees centigrade, the fiber retains about approximately 100% of its tensile properties, whereas after exposure of 1000 hours at 250 degrees centigrade, the percentage of mechanical properties or the percentage of strength that it retains is 73% or 75%. Here is another table which shows comparison of physical properties of meta-aramid fibers from different manufacturers, and we can see that the physical properties of different meta-aramid fibers from different manufacturers are almost comparable. These are the properties which are of Tejan-Connex fiber from Tejan, and we can see that degree of crystallinity in this fiber is about 35 to 39%, and degree of orientation is 90 to 93%, with crystallite size of 3.5 to 3.9 nanometer, and birefringence index is 0.14 or 0.15, and density of the fiber is 1.37 gram per cubic centimeter. Now we discuss the properties of meta-aramid fibers. Since we have already discussed that due to meta linkages, the fiber conformation is irregular, that results in relatively low tensile modulus or tensile strength of the fiber. But meta-aramids are highly temperature stable, and their exposure temperature is approximately 500 degrees centigrade. That means that they can be exposed to 500 degrees centigrade and they can retain their mechanical properties, but their long-term temperature stability is about 220 degrees centigrade. That is, they can withstand working temperature of up to 220 degrees centigrade, whereas one-time exposure can be as high as 500 degrees centigrade. The shrinkage is negligible at high temperature, both in air and in hot water. It is reported to be less than 0.1%. The mechanical properties of meta-aramid fibers are almost comparable with those of commodity fibers, and the meta-aramid fibers are highly sensitive to light exposure and poorly dyeable. Since aramid fibers have intrinsic color, they exhibit yellowish or golden color, but meta-aramid fibers are colorless and therefore they can be dyed. for textile applications. Due to high crystallinity, meta-aramid fibers are temperature stable and they have high melting point and high decomposition temperature. Therefore, they have better thermal properties than commodity fibers, and it is due to this reason that they can retain their mechanical properties at high temperatures compared with commodity fibers. In this regard, although meta-aramid fibers have approximately comparable mechanical properties with commodity fibers, but they can withstand high temperatures and retain mechanical properties at high temperatures compared with commodity fibers. Since meta-aramid fibers are thermally stable, therefore mostly they are used for their thermal stability and not for their mechanical properties. They have high limiting oxygen index. Um, Therefore, they are primarily used for thermal protective applications. Now we discuss applications or uses of meta-aramid fibers. As we have discussed that meta-aramid fibers are famous for their high temperature stability. Therefore, these fibers are used to design protective clothing for the workers which are exposed to hazard of fire. For example, firefighters and race car drivers. It is also becoming standard clothing for workers who operate in chemical factories and other places where the danger of flash fires is real. And because these fibers are inherently flame resistant, abrasion, wear and chemically resistant, therefore the clothing that is made of meta-aramid fibers is durable and can withstand multiple washes. Since mechanical properties of meta-aramid fibers are comparable with those of commodity fibers, that means that they have tensile modulus that is comparable with conventional fibers. Therefore, the clothing that is made of meta-aramid fibers can provide greater comfort as compared with clothing made of other high performance fibers. Since the surface of these fibers can develop anti-static charge, therefore anti-static properties can be improved by blending this fiber with other fibers. For example, meta fibers can be blended with natural fibers that have high moisture content so that their anti-static properties can be improved. Because of their higher thermal stability, these fibers are used in almost all the applications where textiles with higher thermal stability are required. For example, aircraft interiors where fire blocking material is required because regulations require such functionality in these kind of applications. Similarly, in hospital infrastructures, textiles with fire retardant properties are required. Bag filters for a number of industries such as power plants, cement factories and steel factories where the ability to withstand hot corrosive gases is critical. Because meta-aramid fibers are fire resistant, they do not melt and drip and therefore they do not stick to the skin during fire. Therefore, these fibers are used to make clothing for the workers which are exposed to the danger of fire. For example, uh, clothing for the workers of heated furnaces, emergency services workers, fuel handling workers, because these workers are directly exposed to the hazard of fire. Therefore, different type of products, for example, gloves, mitts, work uniforms, aluminized coats and pants, and other kinds of textiles are made from meta-aramid fibers for these workers. Other industrial applications include filtration fabrics, high temperature heat insulants, reinforcement in fire hoses, V-belts and conveyor belts, threads for high speed sewing, and cut fiber reinforcement for rubber composites. Electrical applications include high temperature paper insulation for electric motors, dynamos, transformers, and cables, braided tubing for wire insulation, and dryer belts for paper making, among other applications. Because in many applications, thermal protection is required and requirement of high tensile properties is not important. For example, in electrical insulation and in firefighting clothing. In these applications, tensile properties are not important, whereas fire resistant properties are important. Therefore, in such applications, meta-aramid fibers are a choice of material. However, when other properties such as cut resistance and stab resistance is required other than thermal protection, then these fibers can be blended with high performance fibers like Kevlar that can provide better cut resistance and stab resistance properties. Therefore, meta-aramid fibers in these cases can be blended with other high performance fibers to provide superior properties other than providing thermal protection. Meta-oriented fibers are regarded as first generation of high-performance fibers. Para-oriented fibers are considered the second generation of high-performance fibers. DuPont initiated the second generation with Kevlar, a successor to the first generation nomex. Compared to meta-oriented fibers, highly sophisticated polymerization and production techniques are needed for the para-oriented type to overcome difficulties caused by their rigid molecular structure. Para-aramids such as Kevlar belong to the family of rigid rod polymers. In the next video, we will discuss about synthesis, application, and properties of para-aramid fibers.